Dear students, this is going to be our lecture 4 for the course MMTC 204 and MTH 604, which is basically the basic course in differential geometry. So far we have defined a curve, as you already know, as a function, a vector function alpha from an interval AB, or it could be an open interval also. Okay, an interval to Rn. But we are basically going to study, this n is going to be either 2 or 3. That means the curves that reside inside a plane or three-dimensional space. Okay, so far we have talked about curves and their parameterizations and reparameterizations, and last thing that we did in the previous lecture was the theorem which says that every curve can be reparameterized, has a unit speed reparameterization if and only if it is regular. So that was the last thing we did. We just move a little bit ahead and try to define the curvature of a curve now curvature, whatever it, intuitively we know it is the degree of sort of curvedness of a curve. You would sort of agree with me that this curve is more curved than this one, and the straight line is not curved at all. So whatever our notion of curvature, it should be such that for a straight line it should come out to be 0, right? And of course, and for a circle, say, of bigger radius, it should be smaller. So now this circle is more curved than the bigger circle. So keeping these two things in mind, the most sort of obvious, most straightforward the thing that comes to mind is, you will see that it fits our requirements. And that is, we define the curvature of a curve, and by curve I mean alpha, right? And this time, as I last time told you, that arc length, if we take arc length as our parameter of the curve, then it is automatically a unit speed reparameterization, and we denote it by alpha dash. Now s is the arc length, the parameter of the curve, and we denote it by dash d alpha by ds. And in case we have any other parameter which is not unit speed, which is not arc length, say alpha t, then we denote it by alpha dot t, the differentiation with respect to that parameter. Okay, now we are assuming our curve is unit speed, and it has now if the curve is regular, then it, as the previous theorem said, that it definitely has a unit speed reparameterization. So we can always reparameterize it so that under new parameter, alpha dash, or alpha, the differentiation, the first derivative with respect to the parameter, the length of that vector is always 1 for all values of the parameter. So that is our definition of the curvature. Is if alpha of course would be a function from an interval to Rn. If it is a unit speed curve, which means if it is a regular curve, because if it is a regular curve, we can always reparameterize it so that it is a unit speed curve. Okay, then if it is a unit speed curve with its parameter s, which is usually arc length, almost always arc length. Okay, then the k at s, the curvature at a certain point in that curve at alpha dash at s, is defined to be k of s. The curvature at that point is simply the magnitude of the second derivative of the alpha with respect to s. So that is the definition of our curvature. Okay, now we just move ahead. But in reality, most of the times most of the times the given curve is not in terms of the arc length parameter or the unit speed parameter. So most of the times we have a convenient parameter that makes it easy to define a curve. So we have a theorem in that regard. Now in case we had a parameter different from arc length, then how do we evaluate the curvature at a certain point of that curve? Now in case the arc length is the parameter, then you just differentiate it twice and take the magnitude of that vector at that point. Okay, so theorems is like this, which we are going to do, that let alpha t be a regular curve. Now need not be unit speed, because in case of unit speed we already know how to do it in R3, that means in three-dimensional space. Then its curvature, the formula for its curvature is k equal to alpha dot cross product with alpha double dot in the norm of alpha dot crossed with alpha double dot divided by norm of alpha dot cube. You know what we mean by dot, Alpha dot just means d by dt of alpha, where t is the parameter of the curve. Okay, so let's derive it. It's again very simple. It's just a calculation. Basically we just use a chain rule. Okay, now since it is a regular curve, then we can reparameterize it to a unit speed parameterization. Okay, so that's what we are going to use, because our curve is regular, and by previous theorem we can always reparameterize it in a way so that the new parameter, under the new parameter, the curve is of unit speed. So in the proof we write, let alpha tilde at s be the, we can always do it because it is regular, unit speed reparameterization of the curve. Unit speed reparameterization of alpha. And as usual, let us denote the differentiation with respect d by ds by d by dt by dot and d by dt, by dash. This is the, when I dash alpha, it means that it is differentiation with respect to s, and with respect to any other parameter it is dot. Okay, so now since it is the reparameterization of the given curve, so they are essentially the same curves. Alpha at s is equal to alpha at t. Alpha tilde at s must be the same thing as alpha at t. Of course, different values of the parameter, we just differentiate it and use the chain rule. We differentiate with respect, both sides with respect to t. So I should have alpha tilde dash s into, by chain rule, ds by dt is equal to alpha dot, right? So now k is basically, by our definition, alpha double dash of s, but that means it is d by ds of alpha tilde dash at s, right? Alpha tilde, because this is the unit speed reparameterization. For that, the curvature is already defined to be the double derivative with respect to that parameter, right? Now we substitute alpha tilde dash s from this equation, so it becomes norm of the length of d by ds of, let me write it as alpha dot divided by ds by dt. So we have to differentiate it. Okay, let me change the page. So this is where we have reached. Is it coming in the camera? Yes. Okay, so now we differentiate it. So this can be further equal to, I again use the chain rule. I differentiate it with respect to t, d by dt of alpha dot divided by ds by dt, differentiating this whole thing. Of course, multiplied by, of course, since it was differentiation with respect to s, I should multiply it by dt by ds, or divided by ds by dt. So that would be further equal to d by dt Now I just differentiate. I use the quotient rule. I am differentiating with respect to t. So it should be, what should be? So, okay, you first differentiate the numerator and keep the denominator as it is. So it is ds by dt into d by dt of alpha dot, right? Then I have minus, then I keep alpha dot as it is, and then I differentiate d by dst with respect to t. Okay, so it is d by dt of ds by dt, and this whole thing is multiplied by dt by ds here, and of course we have to divide here by the square of ds by dt, which is just quotient rule of differentiation. Okay, so that becomes now, since when I differentiate it twice, I just put two dots on alpha dot multiplied by ds by dt minus alpha dot into second derivative of s with respect to t, and divided by, I just take it in the denominator, ds by dt ka cube. Okay, now I multiply both numerator and denominator by ds by dt, and you know why. So I can write it as alpha double dot into ds by dt ka square minus alpha dot into ds by dt into d2s by dt square divided by ds by dt ka cube, raised power 4. So this is my curvature of the curve at the point S, at the point T basically, because now a parameter is T. Okay, now we just see what is this ds by dt. Now we know that ds by dt is nothing but the norm of the velocity vector, that is alpha dot, right? So this is my ds by, and if I am looking for its square because I have a fourth power here, so ds by dt square is nothing but alpha dot in norm square, which is the same thing as alpha dot product with alpha dot, because magnitude of the length is the dot, square of the magnitude is always the dot product. Now if I differentiate both sides with respect to t, this equation, I would get this square, so it should be twice ds by dt using the product rule, not product rule, the differentiation, normal differentiation rule. Then I differentiate with respect to inside, so it would be d2s by dt square. This must be equal to, differentiating using the product rule on the right hand side, it would be alpha double dot dotted with alpha dot, and we are going to substitute here. Now this thing is the same thing here. Now this is what we have, so I substitute this here and substitute ds by dt here and here. I get something like this. And I continue. Okay, substituting, I would get k at t is equal to, of course now ds by dt is alpha dot, and then we have times alpha double dot. So it is alpha dotted with alpha dot multiplied by alpha double dot minus, then again this thing is basically ds by dt, d2s, 2 cancels out, so this is basically alpha dot dotted with alpha double dot, because dot product is commutative, so that doesn't hurt us, whole divided by, let's take it down, alpha dot raised power 4. So by substitution we got here. Now using the fact that what we call triple cross product, formula for triple cross product is always it is basically A cross B cross C is always equal to A dot C times B minus for any three triplet of vectors in three-dimensional space. This is the formula for triple cross product. That is A cross B cross C is always equal to A dot C times B and A dot B minus A dot B times C, which implies, so if we use this formula for this expression, it is easy to see that K would be equal to alpha dot cross alpha double dot cross alpha dot. Thinking of alpha dot as A vector in this formula, alpha double dot as B and alpha dot as C again. So we get this thing, whole divided by the length of alpha dot raised power 4, right? Now we know that alpha dot is perpendicular to alpha double dot cross alpha dot, because cross product of two vectors is always perpendicular to both the vectors from which we get the cross product. And for perpendicular vectors, we know that length of A cross B is nothing but length of A multiplied by length of B. So this should be nothing but length of alpha dot multiplied by alpha double dot, length of alpha double dot cross alpha dot, divided by alpha dot raised power 4, and 1 gets cancelled out, which means that K is equal to alpha double dot cross alpha dot whole divided by alpha dot cube. So this way we got our formula for curvature in case the curve is not in the unit speed parameter. In case it is unit speed parameter, so there is no problem. From the definition we will get that it is the modulus of the second derivative with respect to the parameter. There is a problem with light here. Okay. Okay, let me continue further and let's take an example of a curve and evaluate its curvature. And we take a simpler curve, what is called a circular helix, and which is parameterized as alpha t is equal to A cos t B, it is a circular helix, therefore it should be A cos t A sin t B into t, where t is the parameter and of course A and B's are constants. So it would be a curve helix, as you know, this is x-axis, this is y-axis, and this is our z-axis. So it would go like this. So this is our curve, which is parameterized in this way, and we apply our formula to evaluate the curvature of this curve. Okay, now what we do, we just have to apply the formula. We know that K at t at any point is basically alpha dot cross alpha double dot divided by the length of alpha dot cube. So this is the curvature, and it's very easy to evaluate. We just have to evaluate. Now this is the given curve, we just differentiate it once. So alpha dot at t would be, of course, you just differentiate, minus A sin t A cos t and B. We also need the second derivative to substitute in the formula. So alpha double dot at t is we differentiated again with respect to t, each of the components of our vector. So it would be minus A cos t minus A sin t. Of course, B is a constant, so therefore you differentiate it and you get 0. Let me just take the cross product of the two. So you have alpha dot t cross alpha double dot t. The cross product would be equal to, as you know, I, j, k, if you think of it as a determinant. So it would be basically AB sin t minus AB cos t, very easy to do, A square. Now you take this as our I, j and k, then use that determinant thing that you have done earlier. Okay, so this is this cross product, but we have to find its length. Its length would be alpha alpha dot t cross alpha double dot t, the length of this vector would be, of course, square root of a square b square sine square t plus a square b square cos square of t plus square of a square, that is e raised to power 4, which would be basically a square b square you take out, sine square t plus cos square t is 1, so it would be a square b square plus a raised to power 4. You take a square out, that becomes a, and inside you will get a square plus b square, right? But we also have to divide it by the magnitude of alpha dot cube. So that is alpha dot in magnitude would be, just take the magnitude of this vector, so it would be square root of a square sine square t plus a square cos square t plus b square, which would be nothing but square root of a square plus b square. And you divide the cube of this thing, so k should be basically a into square root of a square plus b square divided by root a square plus b square whole cube, right? So this is just a divided by a square plus b square. Very easy. So this is how we found, with the help of our formula for curvature, the curvature of the circular helix. Now it tells us something else. Now it doesn't depend upon t. That means the curvature of the circular helix is same throughout. It's constant. It doesn't change with, you can have a curve like this. Now of course it's less curved here but more curved here, so curvature actually changes from point to point. But in the case of our curve here, the right circular helix, it is 1. It is constant, sorry, it's not 1, it's constant. A, because A and B are both constants in our curve.